In this video, we're going to assess two different proposed mechanisms. So for the reaction of 2NO plus O2 going on to form 2NO2 gas, we've observed that the real rate law is NO squared times concentration of O2. It is third order overall. However, because the balanced reaction would require a single step that was termolecular, this seems unlikely. So there must be some combination of smaller steps that result in this same observed rate law. For the two proposed mechanisms, take some time and analyze them both. See if either of these is capable of returning the real observed rate law, and which step would have to be slow for that to occur. Go ahead and pause. Experiment with these two mechanisms and come on back. All right, well, if you're back, let's start with our first proposed mechanism. What if the first step was slow? Well, then we'd only have to involve that step. Our rate would equal a constant concentration of NO to the first and O2 to the first. That is not going to match our real observed rate. So that cannot be the case. So 1 cannot be slow. If we try that for our second mechanism, well, if we said the first step was the slow step, then our rate would equal some constant NO squared. Well, we got the NO squared part right this time, but we don't have any O2. Previously, we had both chemicals, but they weren't to the correct powers. So far, neither of these is working if the first step is slow. All right, well, what about if the second step is? If that's the case, well, we'd find that there'd be a reaction here that would say that the rate was equal to K of the second step, NO3, NO. Over on our right side, same idea, there'd be some K of the second step times N2O4 and O2. Well, neither of those look like the real rate, but that's because they include the intermediate. So we have to consider what the intermediate is really going to look like. That prior step, we always assume the faster steps are really in equilibrium. Well, there's going to be a rate forwards, which is going to equal the K forwards times NO times O2. And there's going to be a rate reverse, which is going to be the K reverse times NO3. Because we assume the earlier steps are able to reach equilibrium, those rates must be equal, so the two equations must be equal. As a result, we can set this up that the K forward NO O2 must equal K reverse NO3. We can divide the K reverse. This means that NO3 must be equal to this other component, and we can slot that in for NO3. Which means K2 times Kf over Kr, NO, O2 all times NO, which was still there from the outside. This is going to give us a combined K, our NO squared, and O2. That works. Our first step being in equilibrium will bring that NO and O2 down, and so they'll combine with our other NO in the second step, so that our combination of our elementary steps makes our rate look like what we see in the real rate. A constant times NO to the second order, O2 to the first. So our proposed first mechanism could work if the second step was slow. It would return the correct rate law. Just to double check, let's look over at our green reaction. Well, same idea. It's got an intermediate. I need to figure out what that is, because the first step, the faster steps before the slow step, would be considered in equilibrium. We could say that there's a k forward times NO squared, and that must equal the k reverse times N2O4. We'll rearrange, divide k reverse again, and what we'll find is that the N2O4 can be replaced with this component, which means that our K2 times our Kf over Kr times NO squared and the O2 that was there. This would simplify to combined K, NO squared O2. In fact, what we find is that for both proposed mechanisms, if the second step is slow, we will return the observed rate law, the real rate law from experimentation. As a result, from kinetics alone, we can't determine which mechanism this reaction may follow. We can be fairly certain it's not all three molecules combining at once, but we'd have to experiment quite a bit to figure out if there was N2O4 showing up or if there was NO3 intermediate as part of this process. But here's a look at analyzing a little bit. The first step, if that was slow, definitely didn't match the observed rate law. But for both of these, if the second step was slow, when we factor in the equilibrium for the first step, we find that either of these could be a reasonable mechanism.